Welcome to Hydrology, Chapter 2, Lecture 2, Defining the Watershed. I'm Dr. Marty Matlock. We continue to borrow from several sources for this lecture, Forest Hydrology, Fundamentals of Hydrology, and Hydrology for Water Management. Three incredibly good reference documents for you. Recall from last lecture that we described human impacts on the landscape and their impact on hydrology as being fairly consequential, and that the boundaries or the scope of those impacts are usually measured at the watershed scale. We also described the way water moves on the land, and that as we move forward with understanding how water moves on the land and how we can design that movement to meet our purposes, it's important to understand the boundaries within which water moves in liquid form on the land, and that's through the watershed. Because water flows down an energy gradient. You can pump it uphill if you put more energy into it, but generally gravity pulls it downhill, down gradient. The water balance is fairly well defined. The water running off the land, Q, and the water running through groundwater, Q sub G, is a function of precipitation minus all the abstractions on the landscape. And the biggest one of those abstractions, of course, is evaporation. And then evaporation drives the whole process. As we evaluate within a contained area the movement of water, we see that atmospheric vapor storage drops to the surface through precipitation. It's sometimes intercepted through tree branches and leaves, and you have drip and stem flow then down to the surface. Some of that water is evaporated directly back up. Surface water on the surface then is either stored or infiltrated. Water that's on the surface that exceeds storage capacity then becomes overland flow. Infiltration then goes into soil moisture where it's stored, and it can be evapotranspired through plants. Or it can percolate on down to groundwater. Interflow is that subsurface flow that is not quite groundwater flowing to channel storage and flow, or base flow, which is groundwater, which often flows to channels as well, or reservoirs, or the ocean. We can see how water flows on the landscape at a macro scale, at a continental scale, and you could draw basically lines in between all these rivers and effectively define the watersheds pretty well just by drawing sort of middle point lines between all of these rivers. That concept is very much what we use in watershed delineation. So the watershed is the divide separating one drainage basin from another. The problem with the term watershed is it's used too generically. It's not adequately defined to be useful for hydrologists. We generally only talk about watersheds as we talk about sort of the conceptual thing of the drainage basin or the sub-basin. Drainage basin is preferred, and sub-basin. We'll talk about scales of those in a moment. The drainage divide, or just the divide, is used to denote the boundary between one drainage area and another. Used alone, the term watershed is ambiguous and should not be used unless the intended meaning is made clear. So it's okay to say we're going to talk about 8-digit hydrologic unit codes as watersheds and then refer to them as watersheds because you've defined them. Drainage basins are part of the surface of the earth a way to divide the surface of the earth into those areas. Remember I said you could draw lines between all the major rivers of the United States and pretty much come up with the boundaries of their drainages? Here you go. These are the water resource regions in the United States. And you notice that we have, I think, about 22 of these here of the continental United States, 20, maybe 21. I see Puerto Rico is number 21. So this consists of surface streams or bodies of impounded surface water together with all tributary surface streams and bodies of impounded surface water. And notice that the Mississippi River, which covers over half the United States, is broken up. The Missouri River, the upper Mississippi, etc. Notice that each of these have a number. This is the beginning of the watershed zip code which we provide. I would also like to point out that the upper Mississippi River and the lower Mississippi River, these systems are all connected. Flooding in one often will lead to downstream flooding in another. This happens to be the 1993 flood of St. Louis, and this is the 1921 flood down around Mississippi, Louisiana border. Watersheds are delineated by the United States Geologic Service using a nationwide system based on surface hydrologic features, topographic features predominantly. The systems divide the country into 21 regions, those 2 digits you just saw in the major drainage basins. And then within each of those, if you add 2 more digits, that means you can have up to 99 subregions. We don't have 99 subregions in every 2-digit area, but those are because they're divided up based upon geography, not just on equal area. But that results in 222 subregions in the United States. 376-digit basins then emerge. And then when we go to the 8-digit sub-basin, which we typically refer to as the HUC 8, Hydrologic Unit Code 8, we have 2,270 of those in the United States. That's an important number to remember. 2,270 sub-basins, HUC 8s in the United States. Now, Alaska is an odd case. And Alaska is an odd case because when you put Alaska by size over this map of the continental United States, it's huge. It's almost a quarter of the size of the landmass. And so for some reason we don't have a good delineation of Alaska in most of our work. That's a separate set. So Hydrologic Unit Code, consisting of 2 additional digits for each county level system, is used to identify any hydrologic area in the U.S. It's like a zip code. A complete list of these are provided in the USGS Survey Water Supply Paper 2294. And also, you can, at the end of this lecture, you'll see a Find Your Watershed website. Now, these are discretely named and defined areas that have that are critically important for common measurement of land use and water quality and other characteristics. But when we're working as hydrologists, while we are always working in one of these, we're always working in a 12-digit sub-watershed, sometimes across them, sometimes in areas that cross these boundaries. So we're always working within these zones. Our areas of concern are usually much smaller than just, or much more explicit than this, because these are fairly big areas. A 8-digit sub-basin can be 20 miles wide and 50 miles long or 100 miles long. So it can be 2,000 square miles, sometimes even 10,000 square miles. These can get rather large. The 12-digit sub-basins are usually 3 to 5 miles by 3 to 5 miles, so 25 square miles. They're relatively small, but it depends on where you are. So let's extract this process explicitly for a location in California. The Hydrologic Unit Code for most of California is 18. It's called the California region. It consists of a whole lot of rivers. California is a complex state with boundaries of mountains to the east and then the ocean to the west, and large slopes draining to the ocean. There are 4-digit unit code for the northern Mojave, which is a desert area. So we go from 18, we add 2 more, 1809. Now we're in the northern Mojave Mono Lake 4-digit code. And there aren't very many 4-digit codes in this entire area. If we look at this 4-digit code here, see this sort of orangish system, then we can define the 6-digit codes, 180902, the northern Mojave, which is the northern part of that 4-digit code, as this area, 180902. 180901 is to the north of it, so 180902 is the 6-digit code. And then within that 180902, we can have a sub-area, 18090203, Death Valley, Lower Amargosa, this sub-basin. That sub-basin, then this is the 8-digit code, which we would call the subbasin. That subbasin can be divided into the watershed, the 10-digit hydrologic unit code, which we would call watersheds, the Marble Canyon watershed, and then the sub-watersheds of Marble Canyon, the 12-digit code, Upper Marble Canyon, Middle Marble Canyon, Lower Marble Canyon, etc. And you see there are only 4 of these 12-digit codes within this 10-digit code. You could divide it into as many as 99 because you have that many digits to use, but you don't because it's all about the drainage basins and their contiguous flows. These basins are not just defined in the U.S., they are defined globally. And we've worked in the United States with others to help define these. I worked with the European Union and United Nations Environmental Program to define watersheds in Europe, all across the EU nations, as well as in Africa. These are incredibly complicated geographies and sometimes very hard to understand. But interestingly, look at the hydrologic basins of the Sahara, and you look at the subbasins, just a huge number of subbasins in the Sahara. And by the way, I shared this rather colorful map showing the flows and the rivers with different color subbasins because I think it's frankly beautiful, and it's the way you can illustrate the complexity of Earth's surfaces using a number of methods, including artistic flourish. Of course, these are generated using Geospatial Information System tools, GIS, which we will be using in this class. If you've not used them, well, you're going to get to learn. And if you've never used them before, it's going to take some time. And we don't have a lot of time because you only have 5 weeks. So we'll start with the old-fashioned way, topographic maps. Topographic maps are maps of topographic lines in the U.S. That are available free from the USGS. You used to have to go find a vendor and buy them. Every backpacker used to use these as a way to find their way, and engineers also use these as a way to map our locations. You're going to get to use this to map a particular spot in Fayetteville, Arkansas, as part of your homework this week. You have an electronic version of this topographic map available to you. You can zoom in on it, cut and paste it into software, or you can print it out and work with it from paper, however you choose. But let's talk about topo maps. The scale of topographic maps is in minutes, representing the longitudinal coverage. Latitude of Earth are divided into 100 or 180 degrees, half of a circle from pole to pole, measured in degrees north or south from the equator. So the equator is 0 degrees north and south. Longitude, so latitude, by the way, is the measure of north and south. And if you have trouble, and then longitude is east and west. If you have trouble remembering that, just remember the Jimmy Buffett song, if I need a change in attitude, I find a change in latitude, which means he heads south to the Caribbean. So latitude and attitude, he heads south. Longitude's east and west. It's measured 180 degrees east-west from the prime meridian, which happens to be at the port city of Greenwich, England. This is also the reference point for global time, Greenwich Mean Time, or GMT. It was good to be the most powerful empire on Earth during the age of exploration because you got to make all the rules. Each degree contains 60 minutes, which contains 60 seconds. So 3,600 seconds in a degree. And the Earth is 360 degrees around. That gives you a sense of the sort of spatial slices that we take of the Earth in these maps. These maps are typically 7.5-minute maps. That's what you see here. Now, if you ask, well, how long is a second then in terms of meters or kilometers or miles? I can't answer that because I have to ask what latitude are you at? Because as you can see, 360 degrees around the Earth in the northern latitudes at 60 degrees north is a whole lot shorter in terms of kilometers than at the equator. That's just spherical mathematics. That's just geometry. So we can use a nomograph like this, or you can calculate it using arc degrees, but I think it's easier just to use this nomograph. So the distance of unit of each measure and the longitude depends on where you are in latitude. So let's say we're right here, roughly the middle of the United States, and we draw this line across this nomograph, and where it hits the red line up here, that's in arc seconds, then we can say an arc second is roughly 25 meters. And where it crosses the blue line, that's in arc minutes, and we can say an arc minute is roughly 1.5 kilometers. Every minute's roughly 1.5 kilometers. And where it hits the black line, that's in kilometers and degrees. Every degree is roughly 90 kilometers. So you can see that's this area that's covered by this. So it's a 7.5-minute topographic map, and roughly where Arkansas is spans about 11 kilometers wide. So the topographic map I just showed you starts at 94 degrees, 7 minutes, 30 seconds west, because we're west of this point. And it goes all the way to 94 degrees, 15 minutes, because if you add 7 minutes, 30 seconds, remember 30 seconds plus 30 seconds equals a degree. So you're adding, so that becomes 8 degrees plus 7 is 15 degrees. 15 minutes. 30 seconds plus 30 seconds equals a minute. And 30 minutes plus 30 minutes equals a degree. So we go from 7 minutes, 30 seconds plus 7 minutes, 30 seconds is 15 minutes. That's the way this reads. It seems arcane. Well, yeah, that's the nature of it. So what we're going to do is we're going to identify this particular point on Town Branch. But that's just to the east and south of where Highway 16 crosses Business 71, School Street. So we're going to say, let's say we have a project right here at this intersection, just above where these two creeks converge for Town Branch. And we need to delineate the drainage above this site. So how do you do that? That's what you're going to do for your homework this week. So the first thing you do is you mark all the stream channels from that point. You get a pencil or you use your computer program, whatever you're using, and you just highlight them so that you can see Cato Springs up here and you can see this tributary here. And you start highlighting all the streams in the system, because remember with the U.S. you could see basically the watershed divides just by highlighting the streams and looking at the differences. And you do the same thing with all the surrounding streams. And you could use a different color for those to indicate those are different streams. And that gives you a general layout of your system. Then you identify all the hilltops. And the reason this is an easy one to delineate is because it's got lots of hilltops. Look at this. You got Root Hill, Goat Hill, Puddin Hill, South Mountain Hilltop. Now, the way you remember, these topo lines represent ISO lines, isopleths sometimes, but we generally call them ISO lines, ISO meaning the same. So they're ISO elevations. So every one of these lines is a very specific elevation, and you follow that along. If you're walking this, you're walking on flat ground. It's not going up or down. Water flows perpendicular to that. So if you want to know the flow path down this hill, it's just draw a line perpendicular to these ISO lines. That's where water flows. So finding the divide means putting little X's at the tops of each of these hills and then connecting them, connecting the dots. So you draw water flow lines down the hill so you get a sense for the directions of flow. So if you come up here at Root Hill, and so you ask the question, is all this water in Root Hill flowing down to this stream? It may be, because Root Hill is flowing down this way through Dowell Cemetery and through this intersection of South 49, but also it's captured by Cato Springs Branch, which flows all the way down here. So in this case, this hilltop, all the flow off this hilltop ends up on our site. Goat Hill may be this, it looks like the same thing. So if you draw this Cato Springs up here, we're going to have to go all the way back up into Round Top Mountain and all the way back here to Mount Kessler to find the boundary. So we have all of our hilltops, and we can find then our boundaries, because Farmington Branch does not drain into our system, so it's a different one. And so we have to draw the differences between here. And after you've read topographic maps after a while, you get used to seeing where these boundaries are and following, because sometimes the boundaries are straight downhill, but water goes a little bit water goes a little bit one side, a little bit the other, and that's where the differences are. This is relatively easy. Try doing this in the flatlands of Minnesota or western Oklahoma. Sometimes you'll have one line and go halfway across the map to find another line if you're looking at 5-foot intervals of elevation. And so it's hard to figure out which way the water flows at that scale. So you draw the flow lines of your point. You have to have this point of delineation. We also call this a pour point for your watershed. This is the pour point. You have to draw the lines connecting the hill topos around your pour point or point of delineation through the highest areas. Then draw a line connecting the point of then once you've got this, so now you say you come up here to South Mountain and you've got to go back to your pour point from up here. Well, then you have to go from your pour point straight uphill over to your other place and say from your pour point here straight uphill over across as we move across the Fayetteville National Cemetery. So I hope this makes sense to you. You'll have the full map to work from. You're not restricted to just this image. In case I happen to have cut off maybe some of the watershed to the north, you're not restricted to that. So that's one of your homeworks for today. We also use GIS to do this. And I recognize that some of you may never have used our GIS. Well, you're not going to learn any younger. And I'm not going to be too harsh on you with this assignment. I just want you to go through the process of opening and using the software so you understand it. Don't get too frustrated with it. Learning something new is hard, but you're engineers. You learn something new every minute. Homework 3 will require you to delineate the watershed on paper. Now, we will use ArcGIS through the virtual laboratory, the Citrix server that we have with the Biological Engineering Lab. You need to watch a number of tutorials I provided on how to do this, and then I'll provide a tutorial specifically on the homework. I will give you basically a point-and-click menu for how to delineate a watershed based upon the homework. Later in the class, you may need to do this off of a site, depending on how successful we are with this homework, off of other sites. But we have such little time. I really don't have time to spend 2 weeks teaching you how to do something, because that's 40% of the class. But you should have a working knowledge. You'll be able to access this and take a look at these tutorials. You can review the functions. I've given you a number of links to review these tutorials with. They're not hard, but if you don't know how to do something, it's frustrating. So I'll also provide access to Eric Cummings, a research engineer that works with me, who can help you if you hit a hard spot in your map. He's the one who's prepared the tutorials. So he's the one who can explain them best. Further reading and other resources, you can get topo maps from these sites. You can also get access to national global precipitation measurements and stream flow monitoring sites, a really cool site, which we'll explore in another lecture down the road. But just want you guys to start clicking through so you can start seeing the resources you have available. This concludes Chapter 2, Lecture 2. Thank you.